Hello everyone, welcome to the last video of this week. In this part, we will learn how to implement the single imputation methods in R, and we will be using the toy bivariate dataset that we have had in the slides, and I will start by constructing or manually constructing the dataset, and I call it data. Okay, and we have the data set here, and remember the context. We have two variables, pain score and depression score. There are 20 individuals, and while the pain score variable is fully observed, the depression score variable has 5 missing values. Okay, and we have seen that subjects with mid-pain scores are more likely to have their depression score missing, but right now that is not important. And what we will be doing here is exactly what we have done in the lectures or in the last video in the slides, and we are just completing the data set. We are not performing any subsequent analysis. We are not performing the analysis that we would have conducted in case there were no missing values. Okay, we are just completing the dataset, filling in the missing values, and because it's single imputation, for each missing value we are replacing it with a generated value under the different methods. So let us start with mean imputation. For the mean imputation, what we have to do is pretty simple. We will compute the mean of the depression score variable for the 15 individuals with observed scores on the depression score variable, and we will impute each, or we will replace each missing value in the depression score variable by the mean of the observed data. And we already know from last week that we can ignore the missing values on the command mean by using this extra argument na.rm. And if we do that, we already know that we should obtain 15. That's what we have obtained. And here, this is the code to generate the plot that we have in the lecture slides. It's just the scatter plot of the data. The black dots are the observed data, and the red dots are the imputed data. And let us now construct here on R the completed depression score variable. And there are many ways of doing that, and the way that I have implemented it is the following. I will do it in a vectorized manner, and I will use the command if else. And so I'm asking, is dot na a value here in the depression variable? If it's true, so I have an na, a missing value, I will replace the corresponding value by 15. If it's false, so I have an observed value, I will use the observed value that I have in my variable. And if I do this, this is exactly, I know that I have missing values in the first and second individual, and here I have 15, 15. Then I have two observed values, 14 and 11. Then I have two missing values that now are replaced by 15, and so on and so forth. And once I have this completed variable, then I can check, for instance, the standard deviation of the completed variable against the standard deviation of the observed data on the variable, or I can do the same in terms of correlations. And we know from the last part that because we are imputing values with the mean of the observed data, so we are attenuating the standard deviation and also the correlations. And here, this is exactly what we have obtained. This is the standard deviation of the completed variable, 3.37, that compared with that from the observed, 3.9. 3, and the same in terms of correlations. And if I want the correlation of the observed data, I know that what I'm doing is a complete case analysis. And here we must be aware that this is a toy data set. We have very few individuals, only 20 of them, and 5 of them have missing values. So it's kind of hard to draw conclusions that are like set in stone, but we can have an idea of what happens in terms of correlations and standard deviations, okay? And here I have also, just out of curiosity, plotted the kernel density estimate of the observed data in blue, and of course the complete data, because the completed data, sorry, because we are imputing in this case 5 values with their mean 15. I have a bump here on the value of 15. Just I thought it would be interesting to show this plot, but nothing special about it. Okay, so let us now move to regression imputation, and on regression imputation, we know that we have 2 steps. Correct? In the first step, I fit a regression model to the observed data, in this case to the 15 individuals that have observed data on both variables, and I use as response the variable with missing values, in this case the depression scores, and as covariates, in this case I only have one fully observed variable, I use the pain score as a covariate. And in this case I have used a simple linear regression model. We have seen that we have several assumptions here, that the relationship between depression and pain score is linear, that the errors are IID and they are normally distributed with mean 0 and constant variance sigma square, and we will check later whether these assumptions are satisfied or not. For now, we will stick with this simple linear regression model. And so we fit it to the observed data in the first step, and in the second step we use this model to predict the missing values on the depression score variable. Why? Because I obtained estimates for beta 0 and beta 1. I know the corresponding pain score, so I can just compute a predicted score for the depression variable. And we can fit our regression model with the aid of the command lm, and here I'm passing the whole data, and I know that I have missing values in this data set, but last week we have seen that by default the command lm disregards any individuals or with missing observations, and this is exactly what I want to do, because in the first step I want to fit a regression model to the observed data, so it's fine. I want to do a complete case analysis, and this is what LM is doing by default if we pass a data set that has missing values, so it's okay. And I will save the result of the linear model in an object that I have called fit. You can call it what you want, obviously. And if I do summary, I obtain several information. I have information that I need for now are the information that I need for now, sorry, are the estimates of the regression coefficients, beta 0 and beta 1. And I could also extract it more succinctly with fit dollar coefficients. And now what I want to do is I have fitted my model, I have obtained the estimates of beta 0 and of beta 1, and in the last part we have done the calculations somehow by hand, right? I can do all the calculations by hand. Here I only have 5 individuals, so it's okay to do that by hand, but if we have thousands of individuals and we have a lot of them with missing values, it's not very practical to do this by hand. And there are again several ways that we can do this in an automatic fashion in R. Here I have used the function predict. It's a built-in function, and I'm passing the object fit that contains my fitted linear regression model, and I will predict for new data, and my new data is my whole data set. But I will predict for all 20 individuals, but for those who have observed values, I'm not interested in the predicted value, obviously, but I'm doing this because then I can disregard the predictions for those who have observed values in the depression score variable. And if I do this, I know that I should look at the first and second individuals because they have missing values, then the individual number 5 and number 6. And if we compare with the results that we had in the slides, obviously they are exactly the same. These are deterministic results. There is nothing stochastic here. And here is the, oops. And here, if I do, this is the plot that we have. And as we have seen, whereas mean imputation, the imputed values fall on a horizontal line, here the imputed values, they fall on the regression line. And sorry, this is something it's going in with the part of the screen that I'm sharing. Sorry, it should be fine now. Sorry, it was a problem with the part of the screen that I'm sharing. And again, then I created again the completed depression score variable. And in this case, I have done exactly or something similar to what I have done before, but now if I have an NA value, I will pick up the corresponding predicted value. If not, I will just pick up the value from the observed data. And by doing this, I obtain the completed depression score variable. Okay, so this is basically everything in terms of regression imputation, what we need to do in R. And now let us see how to check some of the assumptions. This is like basic stuff on linear models, so you should be familiar with it. If not, there are plenty of books that you can read chapters about diagnostics of linear regression models. And so if I want to check the assumptions of linearity between my response and my covariates and of constant variance, I can check them using the same plot, and it's a plot of the fitted values against the residuals. And this is exactly what I have here. And we know that if there is no obvious pattern here we have very few data points, but I don't think we can see any pattern. So the assumptions of linearity and constant variance are satisfied. And in this case, I think we are okay. And we can also check the normality with a QQ plot of the standardized residuals. We could have used the residuals as well. It's more standard to use, standardized residuals. And if we do this, I don't think we have any problem here as well. Although normality here, it's not that important, but okay, we are checking it anyway. And okay, now let's move to stochastic regression imputation. We know that stochastic regression imputation is exactly the same thing as regression imputation, but we want to somehow restore the lost variability, because for regression imputation, the imputed values, they fall on the regression line, and of course they have much less variation when compared to the observed data. And it's not realistic to think that in case, or that the values that are missing, if they were not missing, that they would fall in that line, right? We expect some variability, and this is what, as we have seen, stochastic regression imputation tries to do. So I look at the prediction and I add some random noise, and I know that the random noise is normally distributed with mean 0, and the variance is the residual variance. And the residual variance, if I look at the summary of my fitted model, sorry. is this value here. And oops, sorry, I'm always moving this. Oops. Sorry, something is going on here while I'm sharing the screen. That seems to be okay. And I obtained exactly the same value, right? This is 3 point, and here I extracted it, so I don't need to look at it and to type the value. I know how to extract it, okay? And if I do this again, I'm predicting for all, or I'm using the predictions for all individuals. I'm adding noise to all to the predictions for all individuals. But then I just retain the predictions with the added noise for those who have missing values, obviously. And this is what I have done. And if we, here I forgot to fix the seed, but I have here the plot with the seed fixed to 1. And this is what we obtain, okay? This is the same plot that we have in the lectures. And we see that by chance, 4 of the points, they somehow are aligned, right? But this is because of the seed that we have used. If I change the seed, for instance, to be 11, I will obtain a different plot. Where is the plot? Let me just... Yes, sorry. I obtained something different, right? I've used a different seed. Now they are no longer, they are still, 3 of them are still aligned, but if again I change the seed, and again, if I see that I obtain different values, okay? Just to make the point that the values that we obtain here depend on the seed. And again, here we have a very small data set, so somehow it's difficult to draw strong conclusions. And finally, just to illustrate, we haven't done this in the last part, but we have talked about hot tech, and we have seen that we used information from the individuals in our data set to impute the missing values. And we have seen that the simplest version of hot tech is just to randomly select one of the individuals with observed values for the depression score variables and use the value of that individual to impute one of the missing values. And here I have done exactly this. I will search for those who have observed values on the depression score variable. And if I do this, I know that these are the individuals with observed depression score, with an observed depression score, okay? And now I know that I have 5 individuals with missing values, and I will select from this ensemble, say, of individuals. I will select one to be the donor for the first individual with missing values, for the second, for individual number 5, for individual number 6, and for individual number 8. So if I do this, or better look here, because I fixed the seed, I know that the donor for the first individual with missing values will be individual number 14. So we will pick up the depression score from individual number 14. For the second subject with missing value, we will pick up the depression score from individual number 9, and so on and so forth for the other 3 individuals with missing values. And okay, this is the simplest version of the hot deck, but we can also look for similar individuals. And here we need to define, or in general, we need to define what we mean by a similar individual. Here we only have one extra variable, pain score, right? So I can think of individuals who are similar in their pain score. And I have thought, this is just to illustrate, okay, I will form two groups of similar individuals, those who have pain score values below the median of the pain score variable, and those who have pain score variables above the median of the pain score. And the median for the observed data, I don't need here, I don't need the equal to true because I don't have missing values, but it's fine because if I don't have missing values, it will just be ignored, okay? So the median is 11.5, and now I will pick up my donors, but from those who have a pain score below 11.5. What I have done before is I just picked up one of the individuals regardless of their pain score, and now I will randomly pick up one that falls in this category, that has a pain score lower than 11.5. And if I look here at the beginning, I know that these individuals, they all have pain score. The third individual, the pain score is 7, 7, 9 for this individual. So I will pick up one of those. And this is exactly what I'm trying to do here. I'm trying to find the individuals that fall exactly in this strata, let's say, that have an observed value for the depression score, because I want to borrow their values, and that belong to the first group, that their pain score is below the median. And if I do that, I know these are the individuals that I can now use to borrow the values to impute the pain score. And remember that these are the ones because all the individuals with, to borrow the pain score, sorry, to borrow the depression score. And we know that all our individuals with missing depression score, their pain score is below 11.5. So I need to pick up from the first group, from those who are similar, who have also pain score below 11.5. And here it's just to illustrate how to perform a simple autodeck. This is simple as well. It's not as simple as the one we have done before, but this is also very simple, and it's just to illustrate how to pick up the donors. Then we complete the data set in the same fashion. Okay, it is everything in terms of single imputation, and we will have the opportunity to practice this more in the next workshop. Thank you.